This is your video for 6.3 definite integrals and antiderivatives. And what I have here comes directly from your textbook. This is table 6.3 that has your rules for definite integrals. So these are different ways that integrals can work together, that we can change them. Some are just things that you need to know to make your life a little bit easier. And so I'm going to run through these. There are 7 total. So I have 3 on this page and 4 on the next page. First one is order of integration. So remember, the entire time we set up integrals, we always said that A was a lower value than B. Well, if you have an integral set up where you were going from B to A instead of A to B, so basically there's a higher number on the bottom than there is on the top, that's actually the negative of the integral. So that would almost be like looking backwards at an integral. So for example, if you're looking backwards and you're starting at the right endpoint and going to the left endpoint, if that area was above the curve normally, you would count it as a negative because it would be the opposite of that. If that area was below the curve, then it would turn into a positive because again, it's the opposite. We put the negative out in front there. The second one is the zero rule. If you have the integral from A to A of any function, that is 0. That means your beginning, your left endpoint, your right endpoint are the same value. The area under the curve has a width of 0, while anything times 0 is going to give you 0. So it doesn't matter what the function is, that integral when you're going from A to A is going to equal 0. And then we have the constant multiple rule. So this works for a number k, or if you just have a negative sign, you are actually allowed to pull any constants out of the integral, put them out in front so you can find the integral first, and then you can multiply by the k whenever you're done. And again, you can do that with a negative sign as well. Number 4 is the sum and difference rule. So if you have 2 different functions that are being added or subtracted, you can actually pull those apart and integrate them separately and then just add the results together. And this was very similar to a formula that we had for derivatives, how we could find the derivative of each piece in a polynomial instead of like having to automatically do them together, and then we could just put them together at the end. The additivity property, this one, I relate this the most to the transitive rule in geometry, where you know if A equals B and B equals C, then A equals C. Well, if you go, again, F has to be the same function here. If you go from A to B and then you pick up from B to C, well, these B values are the same thing. So that's the same as the integral from A to C without having to worry about stopping at B in the middle. This is something that's useful because if you know like what one piece is and you know what the end result is, you can find missing pieces of an integral. And that's actually something we're going to take a look at. If not in an example, it's definitely going to come up in a homework question. The max-min inequality, I do have a picture for this on the next slide because this one is something that can be kind of difficult to wrap your head around unless you really see it and how it plays out. So if max f and min f are the maximum and minimum values of your function, then the minimum of f times b minus a has to be less than the integral, which has to be less than the max of f times b minus a. So remember that rule from the last section, how if you were integrating a constant, how it's the constant times b minus a. That's basically what this is saying. They're saying if you know what the absolute highest point on your function is, and you take that value and multiply by b minus a. So basically you're making a giant rectangle around your curve. The actual integral value has to be less than that giant rectangle because the entire function would fit inside of that rectangle and then there's space that's not used. On the same side, on the other end, if you know what the lowest value of f is on your interval a to b, and again, you draw a rectangle using that as your height, that value, because a lot of the curve is going to be outside of wherever that rectangle is, that value has to be lower than the actual integral value. It's a way to box the integral in between these two different rectangles, the small and the big. And again, I have that on the next slide, so you'll be able to see that in picture form. Then we have the domination rule. If f of x is greater than g of x on a to b, that means f of x is greater than g of x at every possible point. The integral of f has to be greater than the integral of g over the same interval. And on the same thread of thinking, if your function is greater than 0 on the entire interval, then the integral has to be greater than 0. So here's that min-max illustration. You can see I drew this curve here. So the maximum value would be up here at this point. So I drew this great big red rectangle that covers all of that, again, going from A to B. So the red value would be my max rectangle. The lowest value on that point is where this green dot is. So the green rectangle is my min rectangle. The actual area underneath the curve from A to B has to be greater than the green rectangle, but less than the red rectangle. And that's what these are two other illustrations of the min-max rule. So that brings us to example 1, and I'm actually going to stand up, walk over to the board to do these questions. We are going to use the rules that we just went over, given this information, and we are going to find the values that are specified. So for part A, we are looking at the integral from 4 to 1 of f of x dx. Well, I noticed that my bounds don't go in the order that they're supposed to. Instead of going from 4 to 1, I need to go from 1 to 4. But to flip that, I have to put a negative out in front. So this is the negative of the integral from 1 to 4. Well, I know what the integral from 1 to 4 is of f. According to my beginning directions, that's -2. So this is going to be a negative 2, which is a positive 2. Part B, if I want to know the integral from -1 to 4, well, it doesn't tell me the integral from -1 to 4 up above, but I do know the integral from -1 to 1, and I do know the integral from 1 to 4. So just like putting it together, I can also pull it apart. So instead of looking at the overall integral from -1 to 4, I can look at this in two different pieces. From -1 to 1, that is 5. And from 1 to 4, that's -2. So my overall value is going to be 3. For part C, if I'm going from -1 to 1 of 2f of x plus 3h of x, well, I can rewrite this. I can first use the sum and difference rule to separate this into two integrals, and then I can pull the constant out of each of these. So this is equal to 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. Well, from -1 to 1 of f of x is 5. From -1 to 1 of h of x is 7. So this is really 10 plus 21, which is 31. So that's a way for me to find the integral value without actually having to graph anything, because I don't know what these functions stand for. Using the same directions, I want to put these three up here just to go over some of the ways you may try to be tricked. First one is D, the integral from 0 to 1 of f of x dx. Well, 0 is not one of the values that appears anywhere in my integrals. And you might be really tempted to be like, well, 0, that's halfway between -1 and 1. So maybe I can just do half of whatever we have there. But it doesn't work out that way because I have no idea of knowing what f of x looks like. Now, if it says f of x is symmetric to the y-axis, then yes, you could do half. Because if it's symmetric, you're going to have the same area on the left of the y-axis as you would on the right. But this doesn't make that claim. So we would just have to write not enough information. There's not enough information here to claim, to be able to find anything about this integral. The same way with e. The only information I have from h of x is from -1 to 1. I have no idea what the value is outside of that interval. So once again, this is not enough information. For letter F, this is another one where you don't have enough information because of the h. The only thing I know about h is from -1 to 1. Even though I do know the value of f from -1 to 4, there is not enough information to find out the overall value of this integral. That leads us to example 2. We're going to show that the value of the integral from 0 to 1 of the square root of 1 plus cosine x dx is less than 3/2. So the integral 1 plus cosine x dx, I want to show that that's less than 3/2. So in order to do that, we are going to use that max-min property, because the greatest possible value that I can have on this integral, cosine is at its greatest from 0 to 1 at 0. So the cosine of 0 is 1. So the greatest value that I have here is 1 plus 1 times 1 minus 0. Because the cosine can't, on this interval 0 to 1, cosine of 0 is going to be the highest value. There's no other way around that. Which means that my integral has to be less than, because this is like that max f idea, the integral has to be less than the max times b minus a. Well, the max is going to be the square root of 1 plus 1, which is the square root of 2, and times 1 minus 0 is still square root of 2, and we know that the square root of 2 is less than 3/2, because the square root of 2, this is something you should know, it's about 1.41 as a decimal, which means if the integral has to be less than 2, the square root of 2, and square root of 2 has to be less than 3/2, therefore, the integral has to be less than 3/2. This is actually kind of a proof that we just did here, going through and using one of those properties to justify some type of conclusion. I'm actually going to stop this video here now. It's going a little bit longer than I had expected, and I'll start up a part 2 video to pick up with our next definition and then example 3 and example 4. So go back through, rewatch this. There are some very important properties about integrals here, and reach out to me if you have any questions.